John here from Anatomy Bootcamp, and welcome into today's video. In this lesson, we're going to be taking a look at subcortical white matter, studying exactly what white matter is, how to categorize it, and looking at some specific white matter fiber tracts, as well as some of the functionalities. So first off, why is this important to learn? Now, I have a little mini case study. So in this case, I have a 37-year-old patient who comes in complaining of difficulty speaking. You do your initial testing. You conclude that she has intact auditory comprehension. She has good speech production, yet a little paraphasic. So she's adding in a couple of extra words that shouldn't be there. But she has poor speech repetition. So what she's hearing and asked to repeat, there's some sort of disconnect happening. So you order an MRI with a DTI scan to confirm your diagnosis. And we're going to be circling back to this case at the end of this lesson to understand what exactly is going on here. So first, we have a couple of learning outcomes. So by the end of this lesson, you should be able to describe what white matter is, what it is composed of. You should be able to classify fiber tracts into one of three categories, as well as you should be able to identify specific fiber tracts on brain images and brain scans. So let's first start off by discussing what white matter is. So in previous lessons, we've looked at gray matter, which is going to be found in that outer cortical layer. And that gray matter out here, this is going to contain those cell bodies, as you can see right here. And these have little dendrites. They're going to be communicating with each other. But projecting off of that cell body and traveling through the cerebral hemisphere, we have these axons. You can see right here. And these are going to be projecting from the cell body to lower areas or other areas within the central nervous system. And so some of our axons are going to be myelinated while others are not going to be myelinated. So in this example, these solid ones right here, these will be myelinated. These broken up ones, these will be unmyelinated axons. And what myelin does is it helps for quicker communication between cell bodies. So if we zoom into this image right here, you can see these yellow casings around the axon. Well, this is known as myelin, and this is a fatty substance. And this myelin basically insulates the axon. And what this allows for is for rapid communication between ion channels. So if this was unmyelinated, you would have ion channels all the way down the axon. And in order to carry the action potential, you would need to open all the axon channels. Whereas when you have an axon which is myelinated, you might have a channel right here, another channel right here, another channel right here. What this myelin does is it allows for it to carry the action potential underneath this coated area. So this insulated area is going to protect that signal. So it can jump from this signal to this signal. And allows for a lot more rapid communication between cell bodies within the central and peripheral nervous systems. So the TLDR, what is white matter? White matter is just basically myelinated axons. So now we can classify white matter into three categories. We have commissural fibers, projection fibers, and association fibers. So our commissural fibers are going to be like the communicating fibers. These are going to connect the left and the right hemispheres. So you can see right here, this is a big commissural fiber. It's crossing that midline right here, and it's going to connect the left hemisphere and the right hemisphere. So next up, we have projection fibers, and these are going to be projecting up and down the central nervous system. So they're going to be projecting from superior to inferior and vice versa. So it sends information in both directions. So those are projection fibers. They're projecting. And then finally, we have our association fibers, and these are going to associate areas within the same cerebral hemisphere. So we have subsections of those. We have short association fibers, which will connect adjacent gyri right beside each other. We then have long association fibers, which will connect different lobes within the same hemisphere. So let's say we have one here, which is going to connect the parietal to the temporal lobe. So these are our association fibers. And we're going to go into a little bit more detail as we progress through this lesson. So first, let's take a look at commissural fibers, the most notably being the corpus callosum. If you watched the previous videos, you know that this corpus callosum is my go-to landmark when looking at sagittal sections throughout the brain. It is that big, thick bundle of white matter, which is connecting the left and right hemispheres. So you can see, looking at this coronal image, we highlighted this in the previous slide, this right here. This is going to be that corpus callosum, which is going to be connecting the left and the right hemispheres. And if we look at it from a sagittal point of view, we can actually see that it's actually broken up into these 4 distinct regions. So first up, we're going to have the rostrum, which is found at the rostral end of the brain. It's going to be found right here. And then next, as the corpus callosum moves from anterior to posterior, it has to bend. And this bend is called the genu. And genu in French means knee, and knees bend. So that's a little trick that you can help remember it. Then moving posteriorly, we have this long segment, and this is known as the body of the corpus callosum. And this is going to be connecting the genu anteriorly to this portion posteriorly, and this last portion is known as the splenium. So again, we have the corpus callosum connecting the left and right hemispheres, and the corpus callosum divided into the rostrum, that genu, our body, and our splenium. Now, two other commissural fibers, which you might be familiar with from the diencephalon lesson, are the anterior and the posterior commissures, and these are going to make up the boundaries of the hypothalamus and the epithalamus, respectively. So first up, we're going to have the anterior commissure, and it's just going to be inferior and a little bit posterior to that rostrum of the corpus callosum. So you can see I'll highlight it right here. And then moving posteriorly, we have that posterior commissure. The posterior commissure, like we said in the diencephalon video, is going to be at the inferior aspect of our pineal gland. So right here, this is that pineal gland. And then this C shape right here, that's going to be that posterior commissure. And these are best viewed on a sagittal section looking at the midline. They can be seen from coronal sections and horizontal sections, except they're so small that you have to get exactly right on that plane of sectioning. The next structures that we're going to look at are the forceps major and the forceps minor, and these are viewed from a horizontal section. And you'll notice that they look like the corpus callosum, except in a horizontal section, and that's actually pretty accurate because they are part of the corpus callosum, except viewed in a horizontal section. We call this the forceps minor, and we call this the forceps major. And the forceps minor is actually going to be the extension of the genu part of the corpus callosum. So right here, let's call this portion the corpus callosum. You can see we're going to have fibers coming off of the genu anteriorly connecting that frontal lobe area. These are going to be the forceps minor fibers. Similarly, if we look back here, we have the forceps major. This back here would be the splenium, coming off that splenium, connecting the occipital lobe regions. Those are going to be those forceps major fibers. Now, oftentimes students get confused which is major, which is minor. The way I remember it is I look at major. So major has an A, and I come back to my horizontal image, and I see this. Kind of looks like an A, so I just make an A out of it. And this lets me know that this is the forceps major. And then I'll come up here. We have this small m right here. So this is going to be that forceps minor. So the way I remember it, the forceps major has an A in it, so I always draw an A just to remind myself. Now moving on to those projection fibers. So again, these are going to be ascending and descending tracts, which are connecting higher and lower areas of the central nervous system. So in this example we'll walk through, we'll look at a case in which a motor neuron is sending signals from a higher cortical area down to a lower cortical area. So our signal would start out in this outer cerebral cortex area. It would then send signals down these fibers known as the corona radiata. Now these fibers are all going to coalesce and bundle together to form both the internal and the external capsule. So if you remember the internal capsule, it's going to pass within that basal ganglia structure. Then we're also going to have that external capsule, which is going to ride just outside of that basal ganglia structure. Again, this would be the colostrum. This would be our lentiform nucleus. So our external fibers are found between the colostrum and lentiform nucleus. And our internal fibers, well, those are going to be found between lentiform nucleus and the caudate nucleus and thalamus medially. So now that our signals are being sent down, they're going to coalesce once more and join at this area right here in the midbrain and travel down what are known as cerebral peduncles. These are going to take those fibers from the external and the internal capsules, organize them, and consolidate them into tracts, which will then descend down the brainstem and then down the spinal cord. So we have the corona radiata. We also have the internal capsule and the external capsule. And then finally, we have those cerebral peduncles. Now, looking at this image right here, this is an interesting dissection. This is looking at a lateral view, and we've removed some of those superficial gyri. We've removed the whole surface of that outer cortical layer, and we've gone deep, and we're looking at the white matter from a lateral perspective. So let's highlight the corona radiata and the external capsule on here. So you can see this structure. It's kind of radiating out to all areas of the brain. And the corona radiata is like the radiating crown. And you can see why in this image. Going to be all these radiating fibers, and it forms sort of crown, which is going to be extending to all those cerebral areas. And then if we look right here, you can see this would be this region right here. That insular cortex has been stripped away. We've also stripped away this extreme capsule and the colostrum. And we can see these fibers heading in an inferior to superior direction and vice versa. So these are going to be those external capsule fibers. If we went deeper, we would know, because we would hit this lentiform nucleus. We would have to do a very deep dissection in order to hit that internal capsule. So again, we have the corona radiata, and then we have those external capsule fibers. And this right here, this is actually a long association fiber, which we're going to discuss later in the video. So coming back to our internal capsule, looking at it from this horizontal section, you can see that it's actually divided into 3 segments. We're going to have the anterior limb, the genu, and the posterior limb. And like we said, genu equals bend or knee. So highlighting it on this image, here is going to be that internal capsule. And then if we look for that bend, this area right here, well, this is going to be that genu right here. And then just anterior to the genu, we're going to have the anterior limb, and then posterior to the genu, we're going to have the posterior limb. And it's important to know how the internal capsule is divided, because different information travels through each segment, as well as they receive blood supply from different areas, which we'll talk about in future videos. But for an example, the genu carries information which is going to the face. So if we had a stroke in the blood vessel which supplies the genu, well, that would manifest clinically in deficits that we would see on our face. Now, finally, we have our association fibers. We're going to have short association fibers and long association fibers, and these are going to be associating or connecting different areas within the same cerebral hemisphere. So our short association fibers, well, these are going to be connecting adjacent gyri, and you can see these up here. So they dip below the sulci, and they'll connect these adjacent gyri. Whereas the long association fibers, these are going to be connecting different lobes. So these are going to be extending across a longer distance. So you can see here, you'd be connecting the frontal and parietal. Here would be connecting the frontal and occipital. We'd be connecting the occipital and the temporal. So these are going to travel a longer distance. Now, the short association fibers aren't really that special. They're just going to be connecting adjacent gyri. Whereas the long association fibers, these are going to be a little bit more prominent and a little bit more identifiable on a cadaveric specimen. They have individual names, so we're going to be focusing on these ones for the remainder of the lesson. So the first one that we're going to be looking at is our cingulum. And so you can see here, here's another sagittal section. So this time our cingulate gyrus has been removed. So we've basically dissected away this whole area up here. We've gone deep to that cingulate gyrus, and we've exposed the white matter tract, which is going to run parallel to that. And that white matter tract is going to be the cingulum. In that cingulum is going to be that parallel bundle of white matter, which is going to connect the cingulate gyrus to that parahippocampal gyrus. So you can see right here that white matter bundle, it's going to wrap around from the cingulate gyrus in the frontal lobe to the parietal lobe, and then down to the temporal lobe in that parahippocampal gyrus region, and it forms that C shape. So remember, the cingulum is deep to the cingulate gyrus. So now we're going to turn away from the midline, and we're going to be looking at the cerebral cortex from a lateral view. This view, we've removed all the gyri, and we've gone deep into the white matter. So you can see we're going to have a superficial view of that, and then we're going to go a little bit deeper and look at some deeper white matter. So starting off first, we're going to have the superior longitudinal fasciculus. And like the name would suggest, it's superior and it's very long, very longitudinal. It's going to be connecting pretty much all the major regions of the brain. So it's going to be originating here in the frontal lobe. It's going to be connecting the parietal lobe, the occipital lobe, and the temporal lobe. So you can see this purple one right here. This is going to be that superior longitudinal fasciculus. And if we have a superior longitudinal fasciculus, we have an inferior longitudinal fasciculus. This one is going to be found connecting the occipital lobe to the temporal lobe, as you can see right here, and that's going to be inferior to the superior longitudinal fasciculus. And then connecting the temporal lobe, specifically the uncus, to the frontal lobe, we're going to have this uncinate fasciculus. And then last up on our superficial dissection, we're going to take a look at the arcuate fasciculus. And this one is pretty important. This one is going to connect Wernicke's area over here in this parietal temporal region to Broca's area over here in this frontal lobe. And if you remember, Wernicke's area, that's involved in language comprehension, whereas Broca's area is involved in speech production. And this tract right here, this arcuate fasciculus, this is directly connecting those two areas. And then finally, we'll go one layer deeper. So we basically, let's scrap all this. Let's remove these layers out. We're going to go down deep to that corona radiata layer. So here's that corona radiata. And then again, we have that external capsule. These are projection fibers. But we also have this one long association fiber all the way down here. And this is going to be our inferior occipital frontal fasciculus. And this is going to be connecting the occipital lobe to the frontal lobe. It's going to be traveling inferiorly. And this again is going to be deep to this inferior longitudinal fasciculus as well as this uncinate fasciculus, and it's going to travel right there. So now coming back to our case study with our 37-year-old patient who's had difficulties in speech repetition. You can see looking at her MRI, she's got this little lesion right here. And if we're looking at where this coronal section is taken from, it's probably going to be taken from about right here. As you can see, we're going to have some of the parietal lobe, some of that temporal lobe, as well as some of the cerebellum. So you can see the cerebellum is cut right here. So just at this upper boundary of this lateral sulcus, this is where we're going to have that arcuate fasciculus. And if you remember, the arcuate fasciculus, it's going to be connecting Wernicke's area over here to Broca's area anteriorly. And in this patient, we have a lesion which is disrupting this channel of communication. So what this is known as is conductive aphasia or associative aphasia. And in this case, we have a lesion which is damaging the communication between Wernicke's area and Broca's area. So the patient is able to comprehend what is being asked and what is being said and what she wants to say, but she's not able to say it. There's that disconnect from what she understands to what she's trying to say. And this is all caused by damage to the arcuate fasciculus, disrupting that means of communication from language comprehension and language production. So now we're going to take a look at some practice problems to get you guys ready for those bell ringers. So in this first question, question 1 is identify fiber tract A, which is over here, and then classify fiber tract B. So if you guys want, you can pause it and take a crack at it. I'm just going to go ahead and answer it. So you can see fiber tract A is going to be connecting the temporal and the frontal lobes. And if you remember which fasciculus connects those two regions, this is going to be that uncinate fasciculus. And then fiber tract B, well, these are going to be traveling vertically. So if they're traveling vertically, they're most likely going to be connecting a higher to a lower CNS area or a lower to higher CNS area. So these are going to be projection fibers. Specifically, this is going to be that corona radiata right here. So we have uncinate fasciculus, which is fiber tract A. And then fiber tract B, well, this is going to be classified as projection fibers. Now our second practice problem is going to be looking at an MRI scan. Question 1 is identify fiber tract A, which is this one right here, and then fiber tract B is going to be to identify fiber tract B and its classification. So what is this fiber tract and what will we classify it as? Again, you can pause. I'm going to answer them. We know that this is a horizontal MRI section, and we have this kind of V-shaped white matter structure. It's going to be traveling between our caudate nucleus, our thalamus, and our lentiform nucleus right here. And it's got 3 areas. It's got an anterior area, a bend or a genu, and a posterior area. So this fiber tract A, this is going to be our internal capsule right here. And then fiber tract B, well, this is going to be connecting the left and the right hemispheres. So this is crossing that midline. We only have a couple structures which cross the midline. Most notably, we're going to have that corpus callosum, which would be best seen from a sagittal section or a coronal section, but this is a horizontal section. So back here, we would have that splenium of the corpus callosum. And if you remember what is coming off of that splenium of the corpus callosum, there's going to be these commissural fibers, which are going to be connecting this occipital lobe region on either sides. So this is going to be one of our forceps bundles. And if you remember, you always draw that A back here. And A is found in major. So this is going to be that forceps major fiber. And again, it's a commissural fiber. So for question 1, this is the internal capsule. And for question 2, this is the forceps major, which is a commissural fiber. So now we have our last practice problem. Question 1, identify fiber tract A, which is down here. And then we have classify fiber tract B, which is right here. So fiber tract A, it's going to be inferior. It's going to be connecting the occipital lobe to the frontal lobe. So this is going to be the inferior occipital frontal fasciculus. Now, it's not the inferior longitudinal fasciculus because that would be found superficial to this. So that fiber bundle has been removed. And that only connects the occipital lobe to the temporal lobe, whereas this is connecting the occipital lobe to the frontal lobe. So A is the inferior occipital frontal fasciculus. And then B, this is going to be close to that outer gray matter area, the outer cortex. And you can see these little fibers. They're not dipping that far down. They're actually connecting pretty close areas. These are going to be those short association fibers extending between adjacent gyri. So B right here, these are going to be short association fibers. All right, just to summarize everything that we've gone over in this lesson, we know that white matter is made up of myelinated axons. The myelination is what gives it that distinctive white appearance. We also learned how to categorize white matter tracts into those 3 categories. So we have the commissural, projection, and the association. Remember, commissural is communicating between left and right hemispheres, crossing that midline. The projection fibers are projecting superior and inferiorly, and the association fibers are associating with areas within the same cerebral hemisphere. Now at the bottom, I provide you guys with a list of identifiable structures that you should be familiar with and be able to identify on any given brain scan or image. So that's it. I hope you enjoyed that video, and I will see you all in the next one.